Hello everyone, welcome to this lesson. So in this lesson, we're going to go through the Python code for the secant method. Now, if you remember, the secant method is the Newton-Raphson, where we're actually approximating the derivative using a backward finite difference as we have defined in this equation here. And by substituting this derivative in the Newton-Raphson equation, we got a new definition of the XR. And we have described three different iterations of the secant method, and you found out that the only difference is basically we're getting the derivative between a point xi and a point xi minus 1, and based on that derivative we would get the x-intercept, and that would be our approximation, and in this case we got 5, and we replicated this again by getting the derivative between 5 and 4.5 as our representative derivative, and that got us an approximation of 2.88 for the root. And then we did it again, got a derivative between 2.88 and 2.38, and that intercepted the x-axis at 2.08 with an error of 4%. So in this lesson, we're going to be developing a Python code for the secant method. We're going to be evaluating it using an error of 0.1, 0.01, and 0.001. And we're also going to be comparing the result of the secant method with the Newton-Raphson to see if using an approximation of the derivative actually makes a difference. As we have actually seen, it does actually make a difference when it came to here, and we're going to be examining how many applications does it take the secant method to converge to an error compared to the Newton-Raphson. Now, the secant method is actually very, very simple code. As you can see, we are not dealing with the derivative as we have dealt with the Newton-Raphson, so we're going to be getting rid of the dy, and another change that we're going to be making for this. For the Newton-Raphson, we had the initial xi is equal to 1, but in this case also we have a step size because we want to be defining the point before xi to get the derivative. So another change is we're adding h is equal to 0.5 here, but you can define the step size as you see fit. So you can experiment with different step sizes to see if you're going to converge faster to each of the error criteria. Now here the initializations are still the same. Here the header is still the same. If you look at the while loop, the main loop, the only difference here is how I'm defining XR, and I'm defining XR precisely as I have defined it here. You can see is f of xi multiplied by xi minus h minus xi, as you can see here, divided by f of xi minus h minus f of xi. So that's going to be xr, and much like with the previous codes that we've dealt with, here we're defining the approximate error, the true error. Here we are storing the root for the next iteration, and here we are using I to count the number of applications that we are applying for each technique. So let's actually run the code. So what we're going to be doing here, we're going to be replicating what we did here. We used an initial guess of xi is equal to 1, and also we used h is equal to 0.5. So if I run this code, you can find that we have gone through 7 different applications of the secant method. We have gone through or below 0.1% at 0.030907, and you can see the root here is 2.000103. Let's actually compare this back to the secant. If I run this for 0.01, let's actually see. Oh, my bad. Let's actually do 1 here. So here, the Newton-Raphson, if we're dealing with the exact derivative, we have actually converged to the root of 2 after 5 different applications. But when we have used an approximation of the backward finite difference with a step size of 0.5, we have converged after 7. So you can see it took 2 additional applications to actually reach a root below 0.1%. So let's actually examine 0.00. So it's going to take 10 different applications for us to get below 0.001%. And if you remember with the Newton-Raphson, to get below 0.001%, it only took 6, as opposed with this one took 10. So the secant method is a method that is used when you don't have the derivative of whatever function you're dealing with, and the only thing that you know is the function, and you can see this equation is really only defined in terms of the x values and the function values, not dealing with the derivative at all. So it's a very, very powerful technique. It's a very simple technique because it only depends on the function, and it only comes at the cost of applying the technique a few more times to reach the same accuracy as what the Newton-Raphson would do. Now, before I end this lesson, I do want to recap a little bit what is the difference between the secant code and the Newton-Raphson. You can see that I have removed the derivative because we're not dealing with this anymore. I have added the step size here because we're dealing with the backward finite difference. And also the third and final change is now XR is defined in this equation as we have explained here. Now, in the next lesson, I will be describing a very special type of root, which is a multiple root. And we are going to be using the Newton-Raphson and also the secant method to find multiple roots. And we're going to be defining this technique, or calling this technique the modified Newton-Raphson, because we're going to have to modify it slightly to deal with what are called multiple roots. So that's it for this lesson, and I will see you in the next lesson.